Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video demonstrates a very simple machine learning operations or MLOps pipeline for time series forecasting in a home automation farm. Time series forecasting for home automation implies that you can take your telemetry data as illustrated in the image and render it as shown in the next image. While this is a very simple example, it can serve as the basis for your more ambitious home automation projects. So let us get started. The goal of this project is to create an automated, reliable system to forecast domestic water consumption, moving us from reactive monitoring to proactive resource management and anomaly detection. This is not just a one-off script. It's an end-to-end MLOps pipeline designed for stability and continuous improvement. We are predicting consumption 24 hours into the future, hourly. This high granularity allows us to catch leaks or unusual spikes quickly. The table summarizes the 4 key stages. Every step from ingestion to monitoring is decoupled and managed by dedicated Python scripts. This structure makes the system scalable, auditable, and maintainable. Notice how the add underbar ml underbar features.py and train underbar model.py are separate. This means our feature engineering logic can be updated independently of our model training framework. Let us take a quick look at the key scripts. Of course, we will revisit these scripts in greater detail later. So we log on to the database and go into HA, which is our table, and select the table. The water consumption data is retained in this table. And here are the key fields as I've shown up here. And we can look at the properties for the columns. And obviously there is a DDL that we can use to generate it at a later date if we have to. Similarly, there is the hourly water forecast that we can look at, and it's basically the run timestamp, the forecast time, and the prediction value. And we have a DDL for that. And again, we can look into the definition of the columns in here. Right. And if you want to look at the data, it's pretty straightforward. We have some data in here, and similarly for the water hourly, we have some data. So as we do our processing, you will see that these fields come into play in the Python scripts. This slide illustrates the sequential flow of processes essential for end-to-end MLOps. In data engineering, the key activities are data collection, cleaning, validation, transformation, and feature store management. The flow to the next block consists of versioned, validated datasets and features ready for model training. In training and governance, the key activities are model training, hyperparameter tuning, experimentation tracking, model testing, and artifact registration. This stage includes setting up compliance checks and defining responsible AI guidelines before deployment. The output from this block consists of a fully evaluated and registered model artifact, the production-ready model. In inference and deployment, the key activities are continuous integration, continuous deployment pipelines for model serving, A and B testing, canary deployments, and setting up APIs for real-time or batch inference. The output from this block generates live inference endpoints whose performance and predictions must be tracked. In monitoring and feedback, the key activities are tracking model health, latency and throughput, detecting data drift, that is input changes, and model drift, which is performance decay, and monitoring business metrics. This block closes the loop by sending alerts and feedback data back to the data engineering and training blocks to trigger retraining or data schema updates. This is a good example of continuous iteration. Data infrastructure is the bedrock. We rely on MariaDB not just as simple storage, but as a structured feature store and a prediction store. Data store versus prediction store, we maintain two distinct tables. Hourly water consumption is our feature store. It holds historical facts, all our X features, and the actual Y target variable. Hourly water forecast is solely for model output. Hourly water consumption in our feature store. Note the record time, date time unique constraint. This is critical for data integrity, ensuring that we never duplicate a measurement and that our time series index is always clean. Hourly water forecast in the prediction store. This is where machine learning operations, often referred to as MLOps, principles shine. The combination of forecast time unique and the insert on duplicate key update logic means the predict_usage.py script is idempotent. If the script runs twice, the second run simply updates the existing forecast, ensuring that we always have the freshest data without creating duplicate records. The core of successful time series forecasting is encoding temporal patterns into features the model can understand. A tree-based model like random forest cannot natively understand time. We must manually encode the time series characteristics into features it can consume. This extract, transform, and load, or ETL, stage is where most of the predictive power is generated. Encoding time, features like hour of day and day of week are essential for capturing high-frequency cyclical patterns, the 24-hour cycle of domestic use and the shift in behavior on weekends. Autoregression, the power features. The lagged features, especially consumption lag 1 hour and consumption lag 24 hour, are the most powerful predictors. Water usage at hour T is strongly correlated with use at T minus 1 and T minus 24, the same hour yesterday. Trend and noise reduction. Moving averages, MA 3 hour, MA 24 hour, smooth out random noise and help the model detect slow underlying shifts in baseline consumption. Insert underbar hourly underbar consumption.pipeline. This script handles new data ingestion. It takes raw CSVs, applies the add underscore ML underscore features transformation, inserts the result into the database, and finally moves the file to a backup directory. This file movement is the key to the pipeline's idempotency. A file is only processed once. Let us quickly examine two key visualizations that explain how the random forest model can be used for time series forecasting and which historical data points could be most critical for its predictions. The first chart is the time series forecast itself. The second chart is the feature importance. This chart provides a visual evaluation of random forest model's ability to predict future values based on past observations. Original time series is in gray. This underlying line represents the entire synthetic dataset showing the baseline upward trend and recurring seasonality, cyclical patterns that the model must learn. Training data is in blue. This is the portion of the series the random forest model was trained on. The model analyzed the relationship between the lagged values, which is lag underscore 1 through lag underscore 5, and the next value, which is value within this segment. Train and test split, the black dashed line. This vertical line marks the point where the historical data ends and the true forecasting challenge begins. Everything to the right of this line constitutes the testing set. Testing data. True values are in green color. This is the actual observed path of the time series during the testing period. The model never saw this data during training, making it the benchmark for performance. Random forest forecast, the red dashed line. This represents the model's predictions for the test period. By comparing the red dashed line to the green true values, we can visually assess the model's accuracy. In this example, the forecast generally captures the overall trend, but may struggle to perfectly replicate the high-frequency noise or sharp turns in the true data. This visualization confirms that the random forest model can successfully generalize from the training data to make reasonable predictions for the near future. This bar chart provides critical insight into the model's internal decision-making process, demonstrating the relative importance of the input features. The features are on the x-axis. These are the 5 lagged values, lag underbar 1 to lag underbar 5, created during the feature engineering step. Lag underbar 1 is equal to the value from day 1 ago, which is yesterday. Lag underbar 5 is the value from 5 days ago. The importance score is on the y-axis. This is a metric calculated by the random forest model based on how much each feature contributes to reducing prediction error across all decision trees. A higher score means the feature was more influential. For nearly all time series forecasting tasks, the most recent observations are the most critical predictors. The chart visually confirms this principle. Lag underbar 1, which is yesterday's value, has the highest importance score, meaning the model relies on the value immediately preceding the forecast most heavily. Subsequent lags decrease in importance, showing that while data from 4 or 5 days ago is still useful, the information quickly decays in predictive power compared to the most recent input. Insert underbar hourly underbar consumption.py pipeline. This script handles new data ingestion. It takes raw CSVs, applies the add underbar ML underbar features transformation, inserts the result into the database, and finally moves the file to a backup directory. This file movement is key to the pipeline's idempotency. A file is only processed once. The Python script insert underbar hourly underbar consumption.py is the initial data engineering step designed to prepare raw hourly water consumption data for a time series forecasting model like random forest and to insert the resulting feature-rich data into a MariaDB database. It performs data ingestion, comprehensive feature engineering, and database loading like an extract, transform, and load-like process, which are foundational for training a time series machine learning model. The script is set up to run as a scheduled job that maintains an idempotent data pipeline, that is a process that can be run multiple times without changing the final result beyond the initial run. The file discovery process uses a regex expression for the file name. It scans the current directory for new CSV files matching the naming convention, and then it uses the pandas library to load the raw consumption data from the CSV file. After a file is successfully processed and its data inserted, it's moved to a backup directory. This ensures that the same file isn't processed over again on subsequent runs. Let us scroll through the Python script for add underbar ml underbar features.py. So we can select it from the Explorer menu here, and I hope you can see the screen. I've enlarged the fonts. This script requires a bunch of libraries that I've identified here, and you can see the corresponding import statements. If you look on the left window pane, we can see the structure of the script. We have the string SQL column. This represents all the columns in the table where the data will be stored, and that's identified that variable. We have the definition of add ML features. I've kept the name the same, and we go in and define the fields and upload it. So the main purpose of add ML features is to prepare the raw time series data for machine learning and to ensure that it's properly stored. So we use pandas for that, and we fill in all the fields. To transform the raw hourly consumption and time data into a set of predictive features like lags, moving averages, and time indicators that the random forest model can use to find patterns. So we go ahead and connect to the database, set up the configuration information, and then iterate through all the files in a given folder. To automatically detect new CSV data files in a specific input directory and process them. And to implement error handling and file management logic to ensure that data is processed reliably and to prevent reprocessing the same files, what we do is send the files over to another backup folder in case we have to restore it afterwards. So the script achieves its goals through specialized time series feature engineering and robust file handling. We have the time-based cyclical columns, hour of day, day of week, is weekend, and these are useful values to have in case we want to determine where the prediction is for the weekend or for the hour of the day or day of the week. We tell the model what consumption was 1 hour ago and 24 hours ago. This is critical for time series as current usage is highly dependent on recent history and the same time on the previous day. We also have moving averages as a trend. It smooths out noise and captures short-term 3-hour and long-term 24-hour trend or baseline usage. File management iterates over new files and upon successful database insertion moves the original file to a backup inventory. It handles establishing a connection to the MariaDB using parameters in a config file and then uses the bulk insert comments to process the data. This script provides key benefits that make your overall forecasting system reliable and scalable. Machine learning model readiness. The script ensures that both the training data, train_model.py, and the data used for live prediction, predict_usage.py, use the exact same feature calculation logic. This consistency is non-negotiable for accurate machine learning deployment. Item potency and resilience. By moving the processed files to a backup location only after a successful database insert, the script ensures that no file is accidentally processed twice. If an error occurs during processing or insertion, the file remains in the input folder for manual review, preventing data loss. There is separation of concerns. It neatly separates the data preparation logic from the model training and prediction logic, which is a key principle of good machine learning operations design. Essentially, this script is the automated cleaning crew and feature factory that gets your raw meter readings into a state where your random forest model can actually learn something useful. The pipeline uses a random forest regressor due to its robustness and minimal data preparation requirements. There is no scaling needed. We choose the random forest regressor initially for its strong performance on structured data, its immunity to scale differences between features, and its robustness. Data fetch and split. We retrieve all features from the database. The train underbar test underbar split is done with shuffle equal to false. In time series, we must preserve the temporal order. We train on the past and test on the chronological future. Evaluation. We use standard regression metrics. MAE, mean absolute error, gives us the average error in actual consumption units, which is easy for business users to interpret. RMSE penalizes large errors more heavily. Model persistence. We save the model using joblib. The parametric file name is our primitive version of a model registry. By embedding the hyperparameters, n underbar estimators and depth, and a timestamp, we can trace exactly how and when a specific model version was created, which is vital for compliance and debugging. The Python script to train the model is shown on the screen. We did create the feature columns in the previous Python script when we added features. And we've defined a nomenclature for the model file name so that as we store these models over time, we can relate to the model and see which one works best for us. We have the classic database connector and, of course, the credentials. And the system then goes ahead and fetches all the stored data and then goes ahead and performs the model training. So we have a small helper function in here, and we do the split. Obviously, as we discussed before, the test data will be +1, t+1 in our series. We run the model, and we get the metrics printed out and displayed for the user. We simply leverage scikit's random forest regressor and conduct the fitness test. Then we go ahead and clean up the prediction and get the error values. Finally, we take a look at the key features and rank their importance and save the model. The forecasting script runs on a schedule, for example, daily, to produce the next 24 hours of predictions. The objective, this is the go live phase. The predict underbar usage.py script runs on a daily schedule to generate the next 24 hours of prediction, acting as our deployment engine. The challenge is recursive forecasting. Predicting 24 steps ahead is challenging. The model needs lagged features like t-1 and t-24 for the future time steps, but we don't actually have the consumption for those future hours. The solution, we must generate the forecast iteratively. We predict T plus 1 and then use that prediction as the T lag feature to predict T plus 2 and so on. This is a crucial design decision for multi-step ahead forecasting with tree-based models. Saving and reporting. The forecast is stored in the database idempotently. Simultaneously, it generates a visualization via matplotlib showing the latest actuals alongside the 24-hour forecast and sends this report via email using the configuration in config ini. So let us look at the prediction script. And we are going to leverage some of the previous database connection code. And after that, we go ahead and start the basic feature analysis for the prediction. And we're leveraging, once again, a helper function called generate 24-hour forecast. Once we've done that, we can save that forecast back in the database table. And as I discussed in the preceding slide, we step through it 24 times for the 24-hour cycle. We generate the forecast and we save it as a database table with a timestamp of when the forecast was generated, so that if we do have to revisit the consumption forecast for that particular day, we can index it through the date for that forecast. After saving the database, we have a cosmetic function to visualize it on the screen using matplotlib, and then we also send that chart that matplot creates by email to the end user. Let's also look at the forecast versus actual, because this is very important for us to understand how good a forecast the random forest regressor model can create for us. So we will go ahead, since we're saving the forecast in the database, we will simply pull that information over and let matplot do its magic. And once again, after it's plotted it, we see it on the screen, and we also send it as an email attachment to the user. One other step that I've done here that I'm not getting into a little bit of detail in here, but I also have a Streamlit app that goes ahead and publishes this data as a web app that you can then scroll through or browse through a date range to see the forecast versus actual results. And obviously, being Streamlit, we can post it on another web server with the right dependencies installed. And that's something for deployment that I would hope to do in the near future for you. The Streamlit application provides the user interface for monitoring model health and system performance. Prediction is only half the job. The forecast underbar versus underbar actual.py Streamlit application is the window into the system's performance and is our primary tool for detecting model drift. The monitoring function, the app pulls the data from both tables, aligns it by time, and visually compares the two time series. The key metric is MAE. The MAE is only calculated for the overlapping period where we have both the actual and forecast data. This is the only valid way to assess historical model accuracy. Model drift. If the mean absolute error, MAE, begins to steadily increase over time, it signals model drift, meaning the real-world data usage patterns have changed and the model needs to be retrained on new data. Use a guardrail. The now overlapping data message is an essential guardrail. It prevents users from mistakenly calculating a mean absolute error for a future period where actuals haven't arrived, maintaining data transparency. To fully productionize the system, two final steps are recommended. The current pipeline is functional, but to move it to a truly production-grade environment, we must address these architectural enhancements. These are model registry implementation and feature pipeline enhancement. Currently, model deployment is manual. We update a model underbar file name constant. A model registry table would store metadata and a production status. Predict underbar usage.py would then simply query the database for the active model, decoupling deployment from code changes. Store file name, mean absolute error, and a status, which is production, candidate, or archived. The predict underbar usage.py script should query this table for the latest production model, enabling one-click deployment via a database update. The current lagged features are calculated based on the data within the same input CSV file. If an input file is missing the critical preceding hour's data, the feature is missing. We need to implement a check in add underbar ml underbar features.py to query the database for the necessary lag value if it's not present in the current input file, ensuring data continuity. Current state in lagged features, for example, lag 24-hour, are calculated based on data within the new CSV file. The recommendation when calculating lagged features for new data, always fetch the preceding data point from the MariaDB table, which is hourly water consumption, to guarantee accuracy and continuity, especially when processing files that may not perfectly align with the last ingested record. While random forest is a great starting point for time series machine learning pipeline, we should benchmark its performance against the industry standard for structured data, which is XGBoost or Light GBM, to potentially gain further accuracy. Some of the advantages of XGBoost are, but not limited to, higher predictive accuracy via sequential learning through low bias, robust handling of feature importance and non-linearity, built-in regularization and control, speed and scalability. This presentation provided an introduction of the entire pipeline organized by phase, core functions, data flow, and key operational benefits of random forest. The final recommendation is to focus on implementing the model registry and exploring XGBoost to enhance model governance and predictive accuracy. That's all, folks. Thanks for taking the time to view this very long presentation. I trust you understand that it is really important to migrate to a production-ready automated forecasting system for your home automation solution. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance using information in the Forecasting Principles and Practice book by Rob and George. And for the backbone of the preparation of this tutorial from OBS Studio, Kdenlive, LibreOffice, and of course Ubuntu. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for this assistance.